record now? All right, I'll begin with a word of prayer. So, dear Father, we thank you for this day. Thank you for all the visitors here. Pray that you help them to get something out of this class and not be too bored. In my prayer, Lord Jesus, amen. All right, so so I just wanted to show you a token example of how complex eigenvectors and complex eigenvalues can be used, even in kind of an indirect way like this. If I was trying to, and this, of course, is not the right way to solve this problem. If you're in diffie-q, there's a better way, right? But just following the same thing we did the last time, if I let x1 equal y, and if I let x2 equal y prime, then what do I have? Well, I have a system, x1 prime equals to y prime, which is, of course, x2, and x2 prime is equal to y prime prime, which is equal to, apparently, minus 10y minus 6y prime, aka what? Minus 10x1 minus 6x2. So you see what we really have here is a system of two first-order differential equations with a 2 by 2 coefficient matrix of 0, 1, minus 10, minus 6 times x1, x2, right? Now, then what we learned is that we can look for eigenvector solutions to this thing, right? Like, so let's try for that. This is A, right? So what's the determinant of A minus lambda I? What's that look like? Let's see here. Minus lambda, 1 minus 10, minus 6 minus lambda. Indeed, this is lambda times lambda plus 6 plus 10, aka lambda squared plus 6 lambda plus 10. Totally unsurprising if you're in differential equations right now, you recognize that as being the auxiliary equation, right? And then we complete the square. Lambda plus 3 squared plus 1. All right, so we find eigenvalues, complex, in fact, complex eigenvalues, which are what? Minus 3 plus or minus I. Now, as we've discussed, those aren't technically eigenvalues for the matrix if we view it as a real matrix, right? Those are eigenvalues for the complexification of the matrix, right? And we're going to find complex eigenvectors corresponding to this. Let's find them. So calculate. We need to calculate A minus lambda I, that acting on some vector, that's going to be 0. That's what we're trying to solve. Let's see, that's what you got here. You got 3 minus I, 1, and minus 10, minus 6. So I get what? Minus 3 minus I. And then I usually use u and v as disposable variables here, like that. If it bothers you, I'm using the same letter. I'll fix it here, W. There you go. All right. Whatever. So I'm trying to solve that equals to 0. If you trust the math, you only have to look at one of the equations, because you know this is the same. It's actually both of these equations are the same equations, just like, check it out. So like 3 minus I times u plus v equals to 0 is the first equation, right? What happens if you multiply that equation by 3 plus I? What's 3 plus I times 3 minus I? 3 squared minus I squared? 10. So it gives me 10u plus 3 plus I times v. Does that look familiar? It's almost the second equation, right? It's minus the second equation. You see the first equation and the second equation corresponding to the first row and the second row, they're the same equation. Well, that better be the case, right? We're looking for an eigenvector here, which is a solution, a non-trivial solution to a homogeneous equation. If these equations were independent, there'd only be the zero solution, right? And hence no eigenvectors. If you think you have an eigenvalue, and you try to solve the eigenvector equation, and the only thing you can get is 0, you know what that means? That means you don't have an eigenvalue. That's right. So go back to the characteristic equation and search your heart. Something like that. Anyway, so v is equal to I minus 3 times u. You set u equals to 1, then v is equal to I minus 3. Pick your poison. Anyway, the point here, w, the vector w, is equal to 1, and then I minus 3. I would point out that you can rewrite this complex eigenvector solution as being 1 minus 3 plus I times 0, 1. I will refer to this vector as A, and I will refer to this vector as B. That's the real and the imaginary vector parts of the complex eigenvector. Now, a complex solution to dx dt equals to ax is given by what? You just do x is equal to e to the minus 3 plus I parentheses t times w. That is a solution to the complexified differential equation. All right? Because if you differentiate that, it solves the equation by the same argument I showed you last time. So all you got to do then is look at what this is. Well, this is e to the minus 3t times what? Times cosine t plus I sine t. And then the w, well, that's a plus ib. I won't write the details just yet. I mean, it has that format where this a and b are specifically that. Now, here's the cool thing. Whenever you complexify a problem and you solve it, the complexified version of a real problem, well, the complex solution has within it two independent real solutions. They will appear, if the problem is linear, they'll appear as the real part and the imaginary part. And those will separately be solutions to the original problem. So all I got to do is multiply this out and like collect the real part and the imaginary part. So the real part, e to the minus 3t cosine t a minus e to the minus 3t sine t b, that's the real part, and then factor out an I. I've got myself an e to the minus 3t cosine t b plus e to the minus 3t sine t a. This is like the x1, and this over here is x2. The general solution has the form x of t is equal to c1x1 plus c2x2. That is, in fact, the general solution to the original 2x2 system. Let me be explicit. So this is equal to like c1 e to the minus 3t parentheses cosine t times the vector a, which was what? 1 minus 3. And then minus sine t times the vector b, which was 0, 1. And then I do plus c2 e to the minus 3t. I just factor that out because it's everywhere. It's everywhere, man. See here, cosine t. See here. B, 0, 1. Plus sine t. See what we got, 1 minus 3. There you go. That's actually the honest-to-goodness solution to this system of differential equations. Yep.
Just a minor, over the sine t, you should have a little vector.
Oh, no. Yes, how dare I? Thank you. I'm actually thankful. I wasn't trying to be snarky. It's just my default. Now, of course, this x, right? What does it mean? This is, well, it's y and y prime, right? If you translate back to the original problem, it's y and y prime, right? So another way you could look at this problem, and again, it's by far not the most efficient way to solve the original second order differential equation, but you could look at it this way. You get what? Y is equal to what? Y is equal to C1 e to the minus 3t cos t plus C2 e to the minus 3t sine t. And of course, you guys know that that is indeed the solution to the original problem that you learn in that course. Depending on who teaches it, it's either a formula that you're presented or it's something you derive. I personally derive it from looking at the complexification of this problem in an operator form, and I do much the same thing I did in here when I teach diffie-q. But that's that. All right, there's a larger theme here. If you have a problem, it's a real problem, you go look at the characteristic equation, right? You get complex roots. What do? You complexify the problem. You find complex eigenvectors and also generalized complex eigenvectors. And you solve the problem using those and the magic formula. And we're talking about differential equations right now at the moment, right? Then that complex solution, you can extract the real part and the imaginary part. Those will be separate real solutions. And you'll be able to paste together those things to form the general solution. Now, I have lots and lots of examples in the notes. So if I have, if you need more detail, it's all there. You're welcome to ask me more questions about it out of class if you want, but that's about all I have to say here. Now, here's one thing, you guys, like a first order question people always have is like, you only used one eigenvalue. What's up with that? Right, 2 by 2 problem. If I get lambda equals 1 and lambda equals 3, how many eigenvectors do you have to find to diagonalize, to actually carry it out? You got to do 2 eigenvector calculations here. One nice feature about the complex eigenvector case in the 2 by 2 case is once you find one complex eigenvector, the conjugate of that, of course, is the other one, right? And in as much as the real problem is concerned, who cares? You already have all the data you need to solve the real problem. You don't have to go find the other one for minus 3 minus I. It doesn't matter. Even if you did, you just find you'd still find the same vectors, A and B, except you'd find A and minus B, but it's the same data to work with. You don't need it. Any questions? All right. Well, I promise for the rest of the lecture I will keep it real. So enough of this complex nonsense. Let me get...
Something I was wondering about the quiz is, if you don't mind asking a question.
You can ask while I'm erasing. If I can answer it quickly, I'll answer it.
On problem number 3, it looks like your matrix A is 7, 0, 0, 0. Or, so the 3 by 7 matrix, first row 7, 0, 0, second row 0, 4, 7, and the third row 0, 7, 4. It looks like you're meaning for that to have eigenvalue. It looks like that's supposed to be Jordan form, but it's not quite, because the second 7 should be negative 7 if it were.
Which problem are we talking about?
3. Is that supposed to be Jordan form, or is that just...
That's real Jordan form.
But doesn't real Jordan form have a second 7 as a negative 7?
Oh, yes. I'll have to think about whether or not I want to stand by that problem or change that to a minus 7.
Okay.
Yeah, let me think about that after class. I mean,
Yep.
it's a 3 by 3 real matrix. Can you find its Jordan form?
Probably.
The answer is categorically yes. The Jordan form is totally normal. Oh, wait a minute. That's the wrong word. General. General is the word I'm looking for. And I shouldn't say Jordan form, but the real Jordan form is totally general, right? We can find a real Jordan form for any real matrix. But I probably did intend to put a minus there.
Okay.
Let me email the class afterwards where the minus goes, okay? Or I'll decide not to. But thank you. Very good question. Other questions?
If someone already did problem 3 the way it was written before, it's not that way?
Is it, it worked? But what did you find for eigenvalues? Something ugly? Tell you what, I will look at it after class. I'll look at it. And yes, of course, if you've already worked it out with the problem as stated, then I'll take it. Sure, yeah. Oh, no. And so it begins. inner product spaces. Or more generally, Euclidean geometry. So we have been doing much of what we've been doing has been devoid of geometry in one sense or another, and we've been focusing on the algebra, right? So now, in this part, this arc of the course, I'm going to talk about the interface between linear algebra and geometry. And in particular, I'm going to focus on, I'm going to keep it a little bit more abstract. My chapter is a little bit more down to earth. I'm going to be a little bit less down to earth in here. So I'm going to start out with a definition. My definition is V, a vector space over the reals, all right, paired with a function, which we'll say bracket like this, angle bracket. This function is from the Cartesian product of V to the reals. This is called an inner product. Well, this is the inner product. I mean, inner product. Sorry. Inner product. V paired with a function from the Cartesian product of the vector space itself back to R is an inner product space. Inner product space provided couple things. First of all, we need to know that the bracket of x and y is equal to the bracket of y and x. 2, we need to know that if we have x plus y with z, we get the bracket of x with z plus the bracket of y with z. 3, we need to be able to pull constants out of the first slot. So if I have cx, y, I get c times xy. 4, I need that the bracket of x with itself is greater than or equal to 0. And it's 0 if and only if x is in fact 0. Now these are supposed to hold for generic elements, all right, for all xy, for all xyz, all right. Let me not bore you with those quantifiers, I should say. Let me tell you what this is. Let me do some name calling here. This is symmetric. This right here is linear in first slot. All right, there's 2 slots in the inner product. First slot, second slot, that's the terminology that we tend to use. The number 3 here, that's homogeneity, right? In the first slot, technically. And then the last thing is what's called positive definite. Positive definite, what that says is that the inner product of a vector with itself is only 0 when you have the 0 vector. And also it's positive. It's non-negative generally. Okay, this is an inner product. And we can prove all kinds of beautiful theorems about this structure. All right. Now before I do that, though, let me just give you a couple of examples. The quintessential example, the thing that this is all built over, is just Rn. If we take V equals to the reals, Rn, that's a real vector space. And the inner product of x and y, guess what? It's just equal to x dot y. Check it out. Is the dot product symmetric? Yup. Does the dot product, does it have linearity in the first slot? Like, is it true that if you have, for example, if you have x1 plus x2 dot y, is that x1 dot y plus x2 dot y? It is in fact true. If you've had Calc 3, you already know this. If you hadn't had Calc 3, the proof is in my notes. And it's easy to prove. But it's in fact true. Homogeneity, can you pull a constant outside a dot product? Absolutely. if you have the dot product of a vector with itself is equal to 0. I mean, a dot product of a vector with itself, is it positive? I mean, what's the formula for x dot x here? I'll be more explicit. This much I'll show you. X is x dot x, right? That is explicitly x1 squared plus x2 squared plus dot 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 plus xn squared, right? If you set that equal to 0, the only way that can possibly be 0 is every one of those squares is 0. And the formula is in your face, non-negative, right? It's right, okay. So there you go. The n dimension, so this is, when you pair, I should mention, when you think about Rn paired with the dot product, this is known as Euclidean Nspace. Collectively, the pair, Rn with this, think about these as a pair, they're paired together. This is what's known as Euclidean Nspace. You can give Rn different geometries. You can give it a different inner products that aren't quite that. It's possible. I'm not going to go into weird examples like that right now, though. 2. Another example you could give, and this is a little bit more abstract, you could look at v equals to, say, nth order polynomials over the reals. All right, and you could define an inner product on those as follows. You could say the inner product of f of x with g of x is equal to the integral from 0 to 1 of f of x times g of x dx. That actually defines an inner product on the set of polynomials. So anything I can prove generically just using these axioms for dot products is also true for these. So for example, if I calculate the inner product of x and x squared, that would be the integral from 0 to 1 of x cubed dx, which is 1/4. Does that inner product satisfy these axioms? Yes, by properties of the integral it does, right? F times g is g times f, it's symmetric. We have the linearity from just, if you have a sum here, you have a product, then linearity of the integral. And the only way you can have an integral of a function times itself be 0 is what? Think about it, you're adding, if you integrate a function squared, the only way that could be 0 is if the function's identically 0, right? So you can check all 4 of these axioms hold for that example. A third and weird also example, well, I don't think it's too weird, but a third example would be the set of n by n matrices. N by n matrices. On this, we could give the inner product as follows. AB is the trace of AB transpose. Excuse me. Let me deal with symmetry. What did we have for the trace? It's the trace of B transpose A, right? You're like, well, that's not what I want. But here's another thing. Is the trace invariant under transposition? Think about it. If you transpose a matrix, what happens to the diagonal? It stays put. So the trace of a matrix is the trace of its transpose. So this is equal to, oh, I should have done that to start with. I'm an idiot. I think I worked myself into a corner here. Fine. So that's the, I may have done an unnecessary step. So that's what, A transpose B. Yeah, let me try that again. So this is the trace of AB transpose. Transpose, use the trace thing I said first. Then use sock shoes. I don't even have to use the cyclicity of the trace. So that's BA transpose, which is BA according to our definition. Do you know what the formula is here really though? Once I write this formula, you'll be like, oh, well duh. So what this is, if you work it out, if you do the If you work out what this formula actually means in terms of components of the matrices, all it is this. A1, 1, B1, 1, plus A1, 2, B1, 2, plus dot, 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 plus ANN, BNN. It's really just it's a formula which gives you essentially the dot product of the matrices viewed as n squared dimensional vectors. It's nothing more than that. Okay. So this concept of an inner product is pretty general, right? All right. But I hope we have some geometric intuition about Rn. The point of this is whatever geometric intuition we have about Rn, we're going to be able to steal that intuition and also deliver it with surprising consequences to these other kinds of examples. Yeah.
I'm a little lost with
Sorry.
For Rn, is x dot y like the objective definition of what the inner product is over that field?
There are for a given vector space, there are infinitely many inner products that you could construct.
Transformation or whatever.
It's a definition. I'm saying this is a specific example of an inner product on Rn. Yeah. You could do something like, since you asked the question, you could do something like xy2, like the second one, and the formula could be x1, y1 plus 2, x2, y2, plus everything else the same, x and yn. And that would also form an inner product. You could think of it as something like a grading system or something where you give more weight to the second one. Something like that. It could be an example. All right. That's great. There's another important concept that we should keep with us as we're developing this material, and that's the definition of what's called a norm space. A normed linear space. Now, I should have, or NLS. I have not been careful enough here. There's something I should have said, but I should really say a real inner product space. I'm talking about a real inner product space today. You could also talk about a complex inner product space. It's a little bit different. But anyway, another day, one thing at a time. So a normed linear, well, maybe three things at a time. A normed linear space, V, and I guess fine, real normed linear space is a vector space over the reals paired with a norm. What's a norm? Norm is a function from V to the reals that satisfies a few basic axioms. What are those few basic axioms? When you think of norm, intuitively you should think of length. It's a vector length. So its fundamental axioms are, well, first of all, if you have the length of the sum of two vectors, it's less than or equal to the sums of the lengths. It has this triangle inequality. What is it?
I was just trying to understand the symbol for norm. I was trying to see what it looks like.
Oh, that's. I'm just saying it's like, that's a slot. It's empty. That dot just illustrates. Yeah, I mean, it's really the mapping x maps to norm x is the. Yeah. So the norm has to satisfy the triangle inequality. What about the length of a vector? How does that work? If I take a vector and I scalar multiply it, how does the length of the scalar multiplied vector relate to the length of the original vector? Well, the length of c times x, or the norm of c times x, is equal to the absolute value of c times the length of x. So you have this kind of homogeneity. It's not quite homogeneity. It's like absolute homogeneity or something. You pull out absolute value of the constant, right? And then 3. Let's see, what else do you know? We also have that the norm of x is greater than or equal to 0, and 4, the norm of x is equal to 0 if and only if x is equal to 0. So it's again, non-negative, and it's only 0 when it's 0. When I teach advanced calculus, I show that the structure, if you have a normed linear space, if you have a vector space paired with a norm, I show that basically this structure suffices to build calculus. All right. That's first arc in the course is what I do. So it's an important idea. Let me give you a theorem that relates these two things in a really simple way. Once I have this theorem, we'll automatically get examples of normed linear spaces, all right? So theorem, if V paired with bracket is a real inner product space, then if you take V and you pair it with a norm where norm of x is simply defined to be the square root of the inner product of x with x, then defines a normed linear space. So in other words, if you give me a real inner product space, I can automatically construct a normed linear space. I can induce a norm from the inner product. This is the induced norm. So like, so like what I'm trying to say is Rn polynomials, nth order polynomials, and even n by n matrices, these are all normed linear spaces because we can just induce a norm from the inner product. Like, so for example, Pn is NLS, where the norm of f of x is defined to be the square root of the norm of the inner product of f of x with f of x. So like, if you ask me what's the length, oh, I couldn't do it yet. Let's see. Let's find length. Let's find the length of f of x equals to x in Pn x relative to this notion of distance. Vector length. So what do you do? Well, the length of x is the square root of the inner product of x and x, right? Which is the square root of the integral from 0 to 1 of x squared dx in our current setup. Now, Adam, you could also ask the question, what's so special about 0 to 1 here? Why didn't you do the integral from 2 to 3? Or why didn't you do the integral from minus 1 to 1? Or why didn't you, the answer is you could. And those would also give inner products that would be different for the polynomials.
I wasn't sure if you were pulling out the example that you were the right answer.
Yeah. Let's see. Okay, so this integral is a third, right? So square root of 1 over 3. And there you have it. The length of x is, in fact, 1 over root 3 in our current context. So what theorems are known then generically? What theorems are known generically about inner products and norms? There's some special inequalities which are known I should mention. I won't prove, but I probably should prove them, but I won't prove them. The one thing is you have, we'll see here, what are important inequalities? Fun facts. A fun fact is one I won't prove. Let's see here. One thing is the absolute value for a inner product space, the absolute value of x with y is less than or equal to the norm of x times the norm of y. This is the Cauchy-Schwarz inequality. So that's something that's known. Let's see, what else should I tell you about? Do you guys remember unit vectors? What's a unit vector from Calc 3? A vector of unit length, right? So you have that construction here too, right? You can define unit vectors. So if v is not equal to 0, then you can define v hat equal to 1 over the length of v times v. That's a definition, right? That defines the hat, all right? And so in this notation, we get v is equal to the length of v times v hat. In other words, this is the well-known claim we make in Calculus 3. Any vector can be written as a product of a magnitude and a direction. V hat gives you the direction of v. V with the bars is the magnitude. Now, in physics, we do another thing, right? We tend to put a vector on the vector itself, right? And then we have this formula, v is equal to v hat. But that's where v is equal to the length of v. So this is great, but not here, okay? Because, I don't know about you, but the thought of writing a vector symbol on every single vector in this course frightens me. Consider how many vector symbols we have not written in here. This alone is missing 20 vectors. See? There's a time and a place for the vector symbol. The time is Calculus 3.
It's not me. It's not me. It's not me.
I blame Danica. Okay. I was looking for an opening for that, so I found it. All right. So you could prove the Cauchy-Schwarz inequality. The proof is in my notes. Maybe I just prove it for Rn. And the fact that this triangle inequality is true for the norm which is induced from the dot product is not entirely obvious either. The proof of that is also in my notes. I'm not going to go through the proof of those inequalities because, you know what? If I was teaching real analysis, I would do it there, but not in here. No, I refuse. So let's go on. We have more interesting things to talk about. What's the definition? So where this gets really, really interesting is in the study of projections. The study of shadows, really, of things onto other things. And fundamental to that discussion is the notion of orthogonality. So we need to define what does it mean for two vectors in an inner product space to be orthogonal. So what's that? So this definition is going to have a few things in it. If you have V with an inner product, a real inner product space, I should have found an abbreviation for that. The calling a normed linear space in NLS, that's a fairly common abbreviation. I don't know a good abbreviation for this because I'm an idiot. What do you say, RIPS? RIPS, RIPS, okay. Yeah, let's see here. Oh, I am teaching real analysis next year though, you know that?
This is April Fool's Day, so I don't believe.
Very good. It is April Fool's Day.
A question on that. If for some reason Skimborda's left, would you be the teacher?
I have no idea. I think Dan Joseph would like to teach it. Also.
Skimborda's not teaching it next year?
No, he's teaching it next year. I wouldn't ask to teach that course. He has guns. No. No. He that's his baby. No, it's not. No. If you want to talk to me about analysis, past real analysis, I'm happy to talk to you one-on-one. That's where it has to stay. All right. I do a fair amount of analysis in the advanced calculus course that I think is, well, it's the kind I'm interested in, which is really the abstraction of linear algebra as it applies to the study of differentiation and continuity. So it's more the analysis of several variables as opposed to just one. Anyway, let's get back to track here. So if V is a real V is a real inner product space, and if we have vectors, say x and y in V, such that the inner product of x and y is equal to 0, then x and y are orthogonal. And yes, Adam, to answer your question, if we were using different inner products, we would have different notions of orthogonality. You could have two vectors that are orthogonal with respect to one inner product, but not with respect to another. So, I know, right? Yeah, exactly. What does it look like? All right, so orthogonal. Furthermore, if S is a subset of the vector space. Now, this could be a subspace. It could be actually just a finite set. I don't care. Then the perp, as perp, is equal to V and V such that what? Such that V with S is equal to 0 for all S in S. So the perp to a set in a real inner product space, it's the set of all vectors which are perpendicular to that given set. That's another definition I should make. What's another definition I should make? I'm glad you asked. Well, we can talk about two subspaces. If you have two subspaces, if W1 and W2 are subspaces of V, then what would we mean if W1 is perpendicular to W2 means what? What would this mean if two subspaces? What would we mean by perpendicularity of subspaces? Or you could say orthogonality of subspaces. That means that W1, little w2 is equal to 0 for all W1 in W1 and W2 in W2. I think I have other there's a couple more terms I got to make sure I define here before I can say interesting things to you guys. What does it mean for a set of vectors to be orthogonal? I defined orthogonality of two vectors so far. What would we mean by, let me put it up here. Well, let me not. Fine, I'll leave the furthermore. So if, yeah.
For all W1, should it be W1?
Yeah. Hey, there we go. If S is equal to, say, V1, V2, Vk, then S is orthogonal if Vi dot Vj is equal to 0 for I not equal to j. In other words, a set is an orthogonal set of vectors if it's pairwise orthogonal. I think I have one more term to put upon you, and then I can go on and say something interesting. What's that? Yeah.
Should that be just a general inner product instead of a dot product?
Oh, thank you. Excellent catch. Thank you. Now, of course, all of these things I'm saying you could replace with dot products, and that would give you the definition in the context of Euclidean Nspace, right? Which is the first example I think about as I'm developing intuition here. Now, what do we mean? There's one other term. If S is orthogonal and well, let me just, all vectors in S have length 1, then S is said to be orthonormal. If you want an equation to compactly tell you what orthonormality is, given the same S up here, instead of just saying it's equal to 0 for I not equal to j, I could just say Vi inner product with Vj is equal to the Kronecker delta Ij. That would concisely capture orthonormality. See, because when I is equal to j, you have Kronecker delta II, which is 1, and so like Vi is equal to 1, but that says that the length of Vi squared is equal to 1, right? So the length of Vi is equal to 1, and that's true for generic I, so all the vectors have length 1. That condition is orthonormality. Do you know any orthonormal sets? You don't? Oh, man. So you don't know this one. If I have Rn, and I have S equals to, say, E1, E2, En, the standard basis, well, okay, so Ei, Ej is exactly just Ei dot Ej, going back to our standard. That's Kronecker delta Ij. Take it back. You do know this. Okay, good. All right. I feel better. Yes, in fact, part of what makes the standard basis so fun to work with is that it's orthonormal. So, in fact, so this is what's called an orthonormal basis. And an orthonormal basis is what? It's a basis which is also orthonormal. Okay. As mathematicians, we're very crafty with our words, aren't we? Let's see here. So guys, what are some interesting theorems we can say here? Here's one. First of all, the perp of S is a subspace of V. Shall I prove it? Let's prove it. It's a subspace, right? All right. 0, right? Notice that 0 with x is equal to 0. How can I prove that? That's almost, I mean, I erased it, but if you use homogeneity, right? You can put, the 0 vector is 0 times 0, right? So if I pull 0 out, then I've got 0 times the inner product, which is just 0 again, right? So clearly the inner product of 0 with anything is once more 0. Just like you know from the dot product. You take the dot product with the 0 vector, you get 0, right? So that's 0. What does this say? That's true for all x in V, but in particular, that's true for S and S, right? So therefore 0 is an element of the perp. So the perp is not empty. We're using the subspace test, all right? So what do I do next? Suppose two things are in the perp, right? So let's let x and y be an element of the perp, and let C be a number. Consider Cx plus y comma S. Let's let S be a generic element in the set S. Consider the inner product of Cx with S, right? Properties of inner product, we can do what? Linearity in the first spot, pull out the constant. See, I'm tempted to spend a day covering this stuff earlier in the course, partly because I think this makes a nice test 1 question. but I don't know. You guys get overwhelmed. I already do too much there. So anyway, these are what? Why are those 0? Because I'm assuming x and y are in the perp, which means they're orthogonal to everything in S. Those inner products are by assumption 0. So what? So this is equal to 0, so therefore cx plus y is again in the perp. And it follows from the subspace test that the perp is a subspace. What is the perp? This is the normal space to the subspace which contains S. Geometrically, that's what it is. So if S is like a point, if S is like a collection of 3 points that define a plane in 3 dimensions, as an example, the perp to S will actually be the normal line to the plane. But this construction of perp generalizes that construction of normal line to other things. Like if I have a plane in 4 dimensions, the perp will be a 2-dimensional normal space through the origin. Or if I have a 2-dimensional subspace in 10 dimensions, the perp will be a 8-dimensional space through the origin. And well, we're going to build the theorems which explain that more carefully, but that's just the start. The next big theorem, I'm out of time, I know, but the next big theorem we'll prove is that orthogonal, or rather orthonormal, implies linear independent. And guess what? You can take any basis in a real inner product space and take it and you can run it through something called the Gram-Schmidt algorithm, and out pops an orthonormal set. So anyway, and we're going to build idempotent transformations called projections and all kinds of stuff. You'll see. I will shut up. Enjoy your quiz.